Hello, everybody. I believe we are live. So welcome to the latest Cloud Tool Time. Cloud Tool Time is brought to you by the Eclipse Cloud Dev Tool Working Group. So we are a member-driven group who advocate for better standards and of course oversee projects in the area of cloud development, in particular IDE, workspace management tools, and so on. Now, one of the things I love about Eclipse tools, is that they're highly extensible, and that's not just adding extensions, but of course building whole applications on top of them that are applicable to a specific domain. So that's why I find today's talk very interesting. Today's talk is web-based modeling tools with EMF.cloud. And this presentation is by Maximilian Koegel. Maximilian is deeply involved in the Eclipse community. He is project lead and committer on several open source projects and serves on the Eclipse Architecture Council. Maximilian, he's general manager of Eclipse Source, where he's focused on building pragmatic tools, both web-based and desktop-based, including modeling tools. So over to you, Maximilian. Take it away.
Thank you very much for the introduction, Brian. And welcome, everyone. I would like to talk about web-based modeling tools, in particular with an Eclipse framework called EMF.cloud. But before we go to that, maybe one question is also, and a valid question is also, why would you even like to build those kinds of tools web-based? In other areas, web-based tools are very pervasive today already and have been for years or even decades. In web-based modeling tools, not so much. And I would like to at least look at a couple of reasons why that can make sense now. When you have a web-based tool, you get a cloud-based environment, so that allows you to avoid any kind of client installation that you might have now. If you have a modeling tool that runs on the desktop, you can provide some of the things quite easily to people. So for example, accessing something via web link. If you think about a review use case, you can just send a reviewer a link and they get your tool and they get exactly to the spot what to review in a tool. So they don't have to do an installation first, check out something, download something, and all those things. So it can make things a lot more frictionless for users. Also, client updates are simple because basically non-existing, like reloading the browser only. And something that sometimes is also important for modeling tools is there's modeling tools that have quite computation-heavy simulation or analysis parts. So you need clients that are that have enough computing power to run those simulations. And if you run that in a cloud-based environment, that's not the case anymore. You need a machine that's able to run a browser, a modern web browser, but the heavy lifting can be done in the cloud-based backend. If you think about usability, which might have been a contradiction years ago, but today you get a modern UI look and feel in the web browser. And if you think about the programming part, you get HTML5 rather than SWT or SVG rather than GEF. So you get more modern technologies. And finally, if you look at maintainability, and if you think about the life cycle of those tools, which typically have a very long life cycle of 10 plus years, you also have to think about where the technologies that you build your tool on are going to be in 10 years from now. And I think with web-based technologies, you have a more certain path of evolution forward. And last but not least, you will also have a simpler time to find employees that are capable with those technologies. So if you're convinced that maybe you want to go to web-based modeling tools at some point or right now, why is it that you can do that now? And if I even think about things that I probably have said 5 years ago, it became so much easier. So if you think about the state 5 or more years ago, I would probably have said it's tenfold the effort to build the same modeling tool with web-based technology in comparison to desktop-based technology. And that difference has vastly vanished. today, there's a couple of technologies that enable that, and the key enablers for that is Eclipse Theia, which is also part of the Eclipse Cloud ecosystem. It's an extensible cloud IDE, so you can build on that for building modeling tools. Then there's the Eclipse EMF.cloud framework, which is the focus of this presentation today, which allows you to build web-based modeling tools. There's Eclipse GLSP, which is about web-based diagramming. And last but not least, there's Eclipse Shea and also Kubernetes, which allow you to deploy a solution to the cloud. And with all those, it just became so much easier to build those kinds of tools. I already said a lot of times those kind of tools. So what are they? And in our experience, we build those tools on a daily basis. It doesn't matter so much on the domain, on the application domain. So the application domain can be an engineering domain like automotive or aerospace or transportation or machine building. But it can also be things like in the medical domain or in insurances, banking. All application domains essentially have the need to abstract from their reality to be able to run certain analysis or to judge on an abstract level certain aspects of their application domain. So if you're a car manufacturer, then maybe you're interested in the safety aspects of your car, so you'd like to model that. If you're in banking, maybe you're interested in risk modeling certain financial assets that you have. If you're in insurance, you might want to model insurance contracts. So that basically exists in any application domain, but the recipes to build those kinds of tools, they're always the same and at least very similar. And the prototypical modeling tool with the features that occur many, many times in those kinds of features is the following, and that's also kind of our reference of what those kind of tools need to be able to do. And the first feature that those tools need is a workbench. What I mean by that is that you need to have some window management so that you can have multiple windows open or multiple tabs, that you have some menu. You might have a status bar, which shows the status of the tool at a certain point in time. Often enough, you have an Explorer component that allows you to browse resources that you can open in the editors. So that's a workbench that gives you the basis for the tool. And of course, what I forgot is a workspace. So you need some data to work on. Then in many of the tools, you have form-based editors for data entry or viewing data. Often enough, those are combined with a tree component. So you can first browse in the tree and then select something, and then you get a form to view or edit the values of the particularly of the model element that is selected. Then in many cases, to view certain aspects of the model that you have, it is better to view those in a graph-based way. So you have diagram support in many of the tools. So a certain part of the data in the model is being displayed as a graph. Often some aspects are also best displayed as text. An obvious example is source code. Many of those tools also work with source code. They produce source code, or they have some source code that augments the model. But also there can be textual models, because some parts are maybe better represented in a textual DSL. And finally, there is often editors of use for analysis or simulation that show the result of a simulation or an analysis that you run on the particular model. And as I mentioned earlier already, many of those tools also produce value by taking the model and producing derived artifacts from that, often textual artifacts like source code or documentation. So there's generators involved that take the model as an input and create some output from that. So this talk is about EMF.cloud. So I'd like to clarify a little bit about what EMF.cloud is. The goal of EMF.cloud is to enable you to build web-based modeling tools. And it does that by providing you components for the cloud that cover frequent use cases, like the one that we've just seen, and by encapsulating best practices on how to build those tools. And furthermore, apart from only providing those components, it also provides example modeling tools like architecture blueprints. Those demonstrate how you can use the EMF.cloud components And they also demonstrate how you can use other available components in the Eclipse ecosystem and outside and use them to build modeling tools. And finally, it's also an incubator for new web-based components. We will later on see one notable example, the GLSP project, which was incubated within EMF.cloud. Now it's called EMF.cloud, so how does it differ from EMF? It's a totally independent project, but it shares many similar concepts, and that's also the intention. But the components are EMF independent. So you don't have to use EMF prior to using EMF.cloud. There's one component, the model server, which is a little bit special. It defines a common interface to the models, and it can encapsulate an EMF dependency if you have EMF-based models. So basically you load, if you want to use a model server, you can load a legacy, so to say, EMF model, a regular EMF model, on the model server side, and then expose that to the clients through a REST API in this case, so that the clients have no knowledge about EMF on the server side. And this facilitates to reuse EMF-based models if you have an existing model tool. Now, this example products I already mentioned, and today we are going to look at one particular example product. It's called the Coffee Editor. And in this example product, we are going to model coffee makers, just for the sake of an example, and because everyone can probably understand a little bit what a coffee maker is. And this coffee editor comes with features that are close to what I presented before. So it uses the model server to support multiple editors, so that you can edit in different editors, and the editor state always reflects the latest changes. There's a tree editor for structural modeling with forms. There's a graphical editor for behavioral modeling. There's code generation to generate some Java code. There's also a facility to work with the generated source code, the generated Java source code, so to be able to run it and debug it. And there is a textual modeling editor and a model analysis component. All of those different things I'm going to demonstrate step by step in the remainder of this presentation. And I'm always going to explain after the demonstration of the particular feature how that is realized from a technology point of view. And then we're going to move on to the next feature. So let's start with that right away. The first feature that I would like to present is editing in multiple editors at the same time, so that the data is shared, and that is being done with the model server. So let's switch to the demo. What I have here is I checked out the Git repository. URL will be on one of the last slides. It's available on GitHub, and I checked that out, and I'm just going to run it now. And this is going to fire up Theia, because everything we see here is based on Theia. And this is what we get. So we get a browser-based IDE. On the left-hand side, we have an Explorer view that shows the contents of my current workspace. So I have a couple of things in here, a POM file, which is not that interesting, but some superbrewer3000.coffee file, which is my model. And then there is a superbrewer coffee notation file, which is a graph that we're going to see in a minute. And then there seems to be a file for a textual DSL, which we will look into later. I'll increase the font size a bit so that you can better see. And I'm going to open up the first editor. So this is a form-based editor. And in this form-based editor, we can see a brewing unit and a control unit within that, and a workflow, which is about somehow preheating, brewing, refilling water, and so on. This is a form-based editor. We will look into details of that later. And we have a notation file, as I said earlier, and this now represents a graphical view. And as we are in this Theia IDE now, there's also some features that just come from Theia. That's, for example, to be able to rearrange editors, and in this particular example, arrange them side by side. And what I would like to do is show you that those two editors now basically work on the same model state in the backend. So what I'm going to do is I'm going to rename this particular activity here. And if you look carefully before I hit enter, you can also see that this activity is shown on the left-hand side. So it shows here in the tree as drink. And when I hit enter, not only does the diagram relay out, but the interesting part is this is also updated on the other side here in the other open editor. And of course, vice versa. So if I take that away again, you can see that the graphical representation updates. This works across different editors, of course, so you can also do that with the textual editors, and this is the basis for the modeling tool. So if we look into that in detail, why do we even need that model server component? If you think about that from an abstract point of view, you have a model here represented as a graph with edges and nodes. And that model consists of different parts that are shown in different editors. So here, the blue part of the editor is maybe shown in the form-based editor, and this green part is shown in a textual editor, and the purple part is shown in a graphical editor. And sometimes those different boxes also overlap. So some editors obviously also display parts of the model that are also present or that are also displayed in other editors. And in this particular case, the first editor is implemented with a framework called JSON Forms. We will see that later on. The details about how to build form-based editors, same applies to GLSP, which is about building diagram editors. And finally, LSP, which helps us to build those textual editors. And of course, we could just have gone ahead and somehow let the editors figure out themselves how to update the other editors, but that's not a good way to go forward. So that's where the EMF.cloud model server comes into play. So it's responsible for synchronizing those editors. So what are the features of that? The model server loads a runtime state of the models that you would like to edit, and it shares that potentially dirty state. So the state might have been altered over time, but not yet stored onto disk again. And it features a command-based change interface so that an editor can tell the model server that it wants to change a particular part of the model. And it features a notification mechanism via sockets so that the editor can subscribe and get updates on which parts of the model just changed by the changes of other editors. It's a Java-based server. It allows you to, as I already mentioned, reuse existing model implementation. So if you have an existing EMF-based implementation, that's really simple to reuse. And it's based on a popular REST framework. And for the model access, you can use a REST API. So you can create, update, patch, and so on. You can request the models in two different formats currently, in JSON or XML. And there's client libraries that make that simple for you to request those models on the client side. And there's a client library for Java and a client library for JavaScript. If we look at the particular APIs, there's an API to load a model. You initialize the model server for a particular workspace folder, and then you can load or get a model. And there's also other methods available there, so you can also ask for the schema or delete and so on. Then there's an API for subscribing to changes of the model. And the idea here is that the editor can react to changes that have been performed in other editors. Here you can see an example how to do that in Java. And finally, there's also an API to change the model. So you can send, the editor can send commands to the model server. The model server then applies those commands, and we can see a typical run of that on the right-hand side. So we have the JSON Forms editor here, which wants to change something and runs a command and sends it to the model server. The model server then applies that command to the model, so that might lead to the creation of a new node. And all subsart editors also get this command sent so that they can update their states accordingly and also see the new model element. So that was basically the model server for synchronizing the different editors. But what are the editors? And one editor, the first one that we looked at, is a form-based editor. And I'd like to show that a little bit more in the demo. So here we have this form-based editor. It has a tree component so that you can create some trees of components. You can also create new children in here. So I could add a dip tray for a coffee machine, for example. And then depending on the type, there can also be other sub-elements that you can create. So something that's pretty common in modeling tools. So I could add a control unit. And now a control unit can have yet another control unit and so on. And the control unit, if I open that up, has a form that represents the different things that are available here. Sometimes there's more complicated stuff, like I can add RAM here. There seems to be different sizes and so on. So this is a typical form-based editor to be able to enter data into the model mostly. How did we build that editor? So we didn't hand code that, obviously. It was built with a framework called JSON Forms. And for the tree that we saw on the left-hand side, that's an EMF.cloud component for building trees. For the forms, we use JSON Forms. And JSON Forms would be a presentation for itself, but there's an extensive website on that also. In a nutshell, it is about building form-based editors and describing the forms in a declarative way. So in JSON Forms, you have a JSON schema, which is a data modeling standard. And in addition, you have something that's called a UI schema that describes how that form looks like. This JSON Forms-based editor is integrated with the EMF.cloud model server based on a TypeScript model server client API, so that it can request the current state of the model and send back commands. Now to graphical modeling, that was the second editor that we have seen. In the demo, graphical editor was that one. This is an SVG-based editor at the very base level, and therefore it's, for example, zooms very nicely. The editor has the typical actions that you would expect. So you have a palette, and with the palette I can add new stuff here. I can inline edit some of the things, and I can obviously also create edges so that I can say that this is connected to that, if my demo would work. Oh, okay, I clicked on the wrong side. So now I've created an edge between those two. The involved components for building the graphical modeling in this case is the Graphical Language Server Platform, GLSP. And that's, at this point, this is another Eclipse project. And it is like LSP for graphical editors. I'm not sure whether you're familiar with the language server protocol. The idea of the language server protocol, which we will also use later on, is that you can build a textual editor for writing source code without knowing the specific details of the language that this editor is later going to edit. And the language smarts that, for example, allow you to get auto-completion and to get the locations in the source code that contain errors, and the error messages for those errors, and potentially refactorings, and all these language smarts that depend on your language. All of that is then added to an LSP server. So the LSP client is totally language agnostic and only concerned with writing source code. And to be able to produce auto-completions and the like, it's going to get the information for that from an LSP server. And the same idea also applies to GLSP. So the GLSP client is generic. So it does not know the modeling language. In this case, we model a coffee maker, and we very specifically we modeled activities activities of this coffee maker, and the edges were the flows between those activities. But the GLSP client that we just saw in the browser is agnostic of that. It does not know anything about the model. It only knows that it will display some round shapes and some connections in between. And the GLSP client in this case is only responsible for rendering the graphical visualization and for allowing user interaction, while the GLSP server is specific to one DSL. So we have a GLSP server in this coffee editor tool, which is specific to the coffee model. So it knows that, for example, only activities are even relevant for the graphical representation, and that if an activity points to another activity, that means there must be an edge. And so the responsibility of the GLSP server is to map the underlying semantic model that we can, for example, also see in the form-based editor to a graphical visualization. And it's also responsible for synchronizing with the model server. So if you think about the change earlier, when I changed a node in here, this does not only change the graphical visualization, this also changes the semantic model because it changes the name of this activity in the underlying model. So in this case, the GLSP server has to inform the model server about that change. The GLSP is based on another Eclipse framework, which is called Eclipse Sprotty, and provides it with graphical capabilities. If we look at that from a deployment point of view, Theia itself is always deployed in, if you run it in the browser in a cloud-based scenario, there's a Theia front-end component that runs in the browser, and then there's a Theia backend component which runs on Node.js. And you can extend those. You can have front-end extensions. And one front-end extension that we have seen here is the GLSP editor. So this is the editor that displays the diagram. The green components in this graphical representation here is always components that pre-exist out of the box. There's a small yellow border around the GLSP editor. That is because the shapes, the SVG shapes for the diagrams is something you need to customize, or you can customize. So that's not pre-configured. Otherwise, it's just a generic editor. And then in the backend, we have a backend contribution. That's really a custom component. It's a GLSP connector, and it connects to the Coffee GLSP server, which is also a custom component. So if you look at that from the use case point of view, so we double-click that file. That double-click will ask the GLSP connector to open up or to launch a GLSP server for the coffee model, because it knows this extension is registered for a coffee model graphical representation. And then once this coffee GLSP server runs, it can use the GLSP core component to implement the functionality of the GLSP server. And the GLSP server is also responsible for synchronizing with another out-of-the-box component with the model server. So in essence, the Coffee GLSP server, once it's launched, will go to the model server and request that particular model. And it will also subscribe to changes in the model so that it can react by updating the graphical visualization. So if we would run through an entire change cycle, if you open up the GLSP editor, it goes to the connector. The connector launches a GLSP server if none is running for that particular file yet. The GLSP server in turn will go to the model server and fetch the particular model. And the GLSP server will also register at the model server for any changes. If you run a change now, the Coffee GLSP server will be notified by the GLSP editor about that change, and will in turn, if it's not just a graphical representation change, but a semantic change, it will notify the model server about that, and thereby also notify any other connected editors, like we've seen with the form-based editor. Okay, moving on to generators. So you can also generate code in that demo. Maybe I should name that properly. So that's complain now. And what I can do is I can generate code for the coffee model. I just select that, and from the context menu, I select generate model code, and we get a bunch of code in here. Basically, there is one class for each activity that we had earlier. So for example, there is one class for complain or one class for drink. And that's just some pre-generated code. And before I go into that, I should go back to the slides. The generator is already done now, but how did that generation work? For the generator, we used Eclipse Extend, which is a framework for also generating code. And in this case, this is a very good example how you can reuse existing things if you already have a desktop-based tool. And in that desktop-based tool, you might already have a generator. You don't have to rewrite that generator just to be able to use it in the web-based scenario here. So what we did to reuse the existing code generator, we built a jar with Maven. And in that jar, there is the code generator. And the integration that we had to add on top of the existing generator is we added a CLI interface so that you can basically have a main method that runs with a certain parameter. And that parameter will specify where the generator should generate to and what model file it should consume from the workspace. And then basically, I don't have a slide on that. Then basically what happens if you launch that generate workspace command in the front end, it will go to the Theia backend. You will have a backend contribution for the generator. And the generator backend contribution only consists of running the jar with a bunch of parameters, with the current workspace, the currently selected model file, and that's it. And since there is not even any result I need to give back, I'm already done. The only thing I need to do is wait until the generator has populated the workspace with the source code. In this super simple integration, you could think about having, of course, some progress bars and so on, but for the simple integration, that's everything you need to do. Now, once you've generated the source code, you might also want to work with that source code. We have already seen that I opened up this Java editor. But this is really a fully functional Java editor. So I have auto-completion in here. I can do the system out println. Welcome to cloud tool time. Right. You can see that there's also already syntax highlighting. So I'm missing a colon here. There's also refactoring support. So I can take that string here and factor that out into, I don't know, a field in the current method, right? I can, of course, store that on the file system again. And apart from that, I can also run that. So what has been done here, a test case was also generated, super brewer test case. This test case contains a method to run the different activities here. So I think, did we implement that into the complain activity? So I'll put a breakpoint in here. I've done that previously already. So this red thing is now a breakpoint that I can establish, and I can just select debug and start debugging. Now this runs even in a debugger. So I even have a full debugger running here. Don't have many local variables other than the arguments for now. And the debugger has the usual things that you would expect. So I can step into run complain now, right? Can see that it will do some outputs. Can step over. At some point, it's going to execute the tasks. Let's look into that. And now we can see that we get very close to this pre-execute method that we've implemented. Let's step into that. And here we're exactly at the change that we have run. We step over, we'll even see that on the debug console. Step over again, of course, and we see the message that we've dropped in here earlier. So fully functional debugger, Java editing, running code within the IDE. How did we get that working? Well, that wasn't a lot of work, at least not on our side. The involved components here is for the code editor front end. So the editor we've seen in the browser, that's the Theia code editor. And it's based on the language server protocol that I elaborated on earlier. For the code editor backend, that's JDT. So JDT-LS is really JDT, but in a language server. So it's the Java development tools from Eclipse, but wrapped into a language server and running in the backend. For the debugging, it's kind of the same thing. There's a debug extension in the front end, and in the back end, there's a Java debug server. So again, for this, the Theia code editor and the Theia debug extension are agnostic to the particular language. And only in the back end, you need to find components that support your particular language. So that's JDT-LS to support Java, but there's obviously language servers for other languages. So there's language servers for C++, TypeScript, JavaScript, you name it. So that's something that's strongly pushed also by other large organizations like Microsoft, for example. And in the back end, you need to find for the debugging a debug server that talks or that speaks this debug adapter protocol language. So integrating source code is really simple. You just have to find the right components. And in this particular case, they work very well out of the box. Now to textual modeling. I also promised that we have a feature about a textual modeling language in the demo. For that, let's go back into the Explorer. Close up the source code. So here we have a textual file, workflow config. This is about configuring the workspace for an analysis, and this is actually a textual DSL. So for example, it has some probabilities here, and the editor has syntax highlighting. In this case, a probability cannot be larger than 1. And there's some assertion here. So this is supposed to be an assertion language that makes sure that in the actual activity flow, check dip tray is performed before brewing. And this also has auto-completion. So it knows that I can only use activities here. And these are the actual activities from my model. And yeah, I can add some other. You need to drink before preheating, which obviously doesn't make any sense. But this is a textual language that's fully functional with auto-completion and syntax highlighting. Now for the textual modeling, the involved frameworks are Xtext. And how does that work? Well, in the browser, Theia front end, in Node.js, Theia backend, as we had before. This time, again, the LSP editor. So the LSP editor is exactly the same editor that we have seen for editing Java code. The only difference is now with an LSP connector, it connects to an Xtext LSP server, because the language that we edit now is not Java anymore. The language is a specific DSL that was built with the Eclipse Xtext framework. And the Xtext LSP server is a little bit of a special component. It's mostly green because it's just generated by the Xtext framework. The only thing you have to give the Xtext framework for that is a grammar that describes your DSL. And the other thing we added to that is a task provider, because somehow this Xtext editor needed to know what are the available activities or tasks from the actual semantic model of the coffee maker. And the task provider, the only thing it does in our implementation is it goes to the model server, gets all the tasks or activities, and then feeds that back into the Xtext server basically as text tokens for the auto-completion. So very little code, but very powerful editor. again, as I said, the text editing is done with the Theia editor. So that was the same one as for Java. The LSP server was generated with Xtext, and the integration is this time with a Java-based model server client API to request the tasks from the model server. Model analysis. For the model analysis, we can run an analysis on those activities. Just going to revert my changes because I don't know how the analysis will look like with those erroneous additions here. And I can perform the analysis based on this workflow config here. And it will provide me with an HTML view of an analysis of the available execution paths. So we can see that when you start, 100% of the executions need to go through the push activities, check water 100%, and then we're divided. Either we need to refill water or water is okay, and then we can go on to check dip tray and so on. This is just an example for one analysis that you could run on that. There could be more complicated ones, obviously. And that was built with a very neat non-Eclipse framework now. It's called D3. And it's about visualizing data in the broadest sense. And it has if you want to take a look, if you don't know it, it has very nice demos on what it can visualize. And the visualization that we have just seen, we didn't code that. That's just done with D3. For the analysis, one of my colleagues insisted on using Kotlin for the sake of an example of using a different language yet again. So it's also easy to integrate components with different languages for your solution. So the analysis is some Kotlin code, and basically it just needs to provide these execution paths by looking at the model, by looking at this workflow model. And the integration is again a Java-based model server client API. Now, I've mentioned it a couple of times, but I wanted to make that an explicit slide. You might start Greenfield and then you don't have that problem, but many people don't start Greenfield. They already have a desktop-based solution that needs to migrate somehow. And the best advice I can give you from seeing that happen at different customers and also seeing it failing at customers of ours. So often enough, unfortunately, we come to the projects when they already failed to do that once. And that's one strategy that is particularly dangerous that I've seen, and that's a strategy to say, well, we need this new web-based tool, and we have the existing desktop-based tool. So what we're going to do is we freeze the desktop-based one. We're not going to change anything there anymore, and we just develop a new web-based tool. And then we have to develop the web-based tool until we reach feature parity with the desktop-based tool, and then we're going to migrate everyone, and that's that. And that just doesn't ever happen. Most of the time, the feature parity is just never reached with the web-based tool. And there's various reasons why that happens. But if you just think about it, if you would keep your development team constant and just split it into the people that still have to maintain the desktop-based tool, people have to develop the new web-based tool, you don't have a lot of resources by that. And then other things happen. You need to add some features to the desktop-based tool still because customers of yours are asking for that. Technology evolves, you have to change something in the desktop-based tool, and suddenly you are in a race between the desktop and web-based tool. And the best way to avoid that is an iterative migration strategy. And the idea of that iterative migration strategy starts with first defining a strategy. That means defining when do you actually want to move to a web-based solution, because that could be far in the future, and nevertheless, it already makes sense to define that strategy. I'm going to get to that in a minute, why that makes sense. And a time plan, so that you know, okay, when am I going to do that, and which steps am I... Apologize, my dog is barking at the doorbell. And what also makes sense is to get a feeling of how complicated that will be to already build a POC that underpins your strategy. And that is, in my mind, something that any tool project needs to do, unless you already know that you will deprecate your tool quite soon. Because I think over the long run, this will become unavoidable. It's really hard to put a time on that. If you ask me, I think in a 10-year framework, in a 10-year time frame, it's quite certain that you have to move to a different technology, to a web-based technology. So you need that strategy. Why do you need it now? I think you need it now because it can make a huge difference for architectural decisions in your desktop-based tools today. Because if you add a new feature, you can add the new feature in a way that will make it very simple later on to move it to a web-based solution, or you can add it in a way that will just add additional complexity into a later migration. So examples for that are, if you can, you will run things headlessly. So you will have a lot of headless business logic that you can trigger from a web-based or a desktop-based solution. You can try to single source things. You can try to even retrofit web-based solutions. So you build a new feature based on a web-based solution. A good example would be the analysis feature we have just seen. Maybe it's even simpler to build that with a web-based framework like D3. And to be able to use it in the desktop-based solution, you can run it in a browser widget within the desktop platform like RCP. So there's a couple of different tools or strategies or tactics to be able to make architectural decisions in a way that they don't hamper your ability to migrate later. Then in the midterm, you might even do some architectural changes proactively to prepare the migration. One example would be that you move to declarative artifacts for things like the form-based editors. Another midterm activity could be to migrate high-value use cases. So I mentioned the review use case. I see that in a lot of tools, the review use case is high value in the sense that it profits a lot from a web-based interface, because people can review things quite easily without having to install a tool and get the right data. And you can start to single source components, as I already mentioned. And on the long term, at some point, you will start your migration project and migrate use cases, use case by use case, but also do that in an iterative fashion. And that might sound super, it is actually difficult, but it's less difficult than this migration race between an entirely new code base. And the idea here is always that if you migrate a use case, you still allow this use case to run with the same code base in the desktop-based tool to the largest extent possible, because otherwise you get into this maintenance hell. And then at some point, when you've migrated enough use cases, maybe you don't need exact feature parity, you deprecate the desktop-based solution. So in summary, we've looked at EMF.cloud, which was about building web-based modeling tools, and there's components in EMF.cloud to build so in a more effective way. There's also example products I've mentioned, or I've not mentioned, I've shown you one of those products, the coffee editor. It's available on GitHub. There's another product, an eCore editor. eCore is the data definition format of EMF. So there's also an editor available for that as an example. And what I hope that I brought across is that it's much more simple today to build web-based modeling tools. It's really feasible today, and reuse and migration are facilitated by those existing frameworks. If you would like to test out the demo that I've shown today yourself, there's a live demo available on the link on the slides. So you can even, it's deployed to a Kubernetes cluster, so you can just try it there, and more information on EMF.cloud is available on its website. If it's the only takeaway, I think if you have a tool that you would like to maintain, then you need to think about how that could go into a web-based scenario on the long run for the reasons I've just mentioned on the slide earlier. And with that, I would like to conclude, and I think we can still have a couple of minutes to go into a Q&A session. So if there's any questions, please go ahead.
Yes, thank you very much, Maximilian. There certainly is time for questions. So let's start with a couple that have come in from Sood on the chat. He says he's looking forward to learning about the following. First question, how does EMF.cloud fit into a GLSP client plus Theia plus GLSP server plus J architecture?
Mm-hmm. Let me answer that with a slide, which is, I'm still streaming, am I?
Yes.
Yeah, like that. So EMF.cloud would provide you with the model server component if you want to use Theia GLSP. The model server component would serve the semantic model. So in our case, that was the available tasks of this coffee model. The GLSP server, you're probably aware what it does, and the GLSP editor. And the GLSP editor and server run in a Theia context. So the GLSP server is a Theia frontend contribution. The GLSP connector and the server at launch is the Theia backend contribution. So they run on Node.js or within the browser respectively. And now for the broader context, all of that, this entire stack can now be deployed into J and effectively thereby into Kubernetes, in the sense that, I think I even have a backup slide on that. Yeah, like here. In the sense that in J, you have a J server node that allows users to access a workspace. And this particular workspace also contains the runtime technologies that are required to do so. And it also includes the IDE. And this IDE in this case would be the Theia IDE, including all the contributions that make up our modeling tool here. So for example, the GLSP frontend contribution. So by using J, you take this Theia-based solution and make it a cloud-based solution that is accessible to people via the browser and offers them different workspaces. So I hope that answers the question to some extent.
And I think the next question you covered in the last few minutes of your presentation. What is a potential path of transformation of an existing Eclipse ORCP-based domain-specific modeling and diagramming application to being web-enabled?
Mm-hmm. Yeah, that's a very good question. So as I try to very roughly sketch, the idea that I would have for such an endeavor would be to do it iteratively. So that means you need to pick a component. Let's say you want to revamp your analysis component, and you would migrate that component to a web-based technology, and then in this case retrofit it into the desktop-based tool inside a browser widget. But that really depends on case by case. Take another example. Let's say you have a form-based editor. A form-based editor based on, in this case, SWT essentially. You would, in this particular example, maybe want to move that to a component called EMF forms, which gives you a declarative artifact that defines the forms. So it becomes simple to also render that declarative artifact within a browser by using another framework that we touched today, JSON forms. So the solution for one particular component really depends on the component, but your goal must be to find a way to single source that component so that you can use it in your desktop-based and your web-based solution at the same time. Because only then you have a chance to maintain those two variants of your tool at the same time. And in EMF.cloud, as I mentioned, there is a couple of components like the model server that if you have an RCP plus EMF-based tool that make it simpler to run this kind of transformation. I think what probably helps you in better understand.
Go ahead.
What probably helps in better understand, because that sounds very theoretical, right? Is this really possible? But I think if you have a concrete tool, one of the best things you can do to be able to actually write a sensible strategy is to build a proof of concept. And in the proof of concept, you will see how that's feasible for your components. And obviously, that's also something we can help you with as a company. But there's also a lot of material on the web how to do these kinds of things. The only thing I would really strongly advise is try to do it iteratively, because the other path always looks good in the beginning because you will make some fast progress, but you will just never complete.
A semi-related question is, when do you expect RCP to become deprecated?
That puts me in a hot seat. So that's just my gut feeling. I'd say 10 years. So I think in 10 years, there might be still an occasional fix here and there, but not a lot of people will be maintaining RCP applications anymore. And on the same notion, SWT-based applications. This will really be legacy by that time, I think. And if it's legacy, it comes with other problems, right? Do you still get security fixes in time? What is if you have a bug? Can you find someone who's still knowledgeable with that technology? Is there still a big ecosystem around that, right? You know, is there testing tools for SWT that are still maintained? So I think, yeah, I'd say 10 years. Quote me on that if it's not the case in 10 years.
I'll put it in my calendar for 10 years then. I want to leave a little time just for some housekeeping issues for our attendees. So I'll just throw in one more quick question, if you could answer it. Does it make sense to use EMF.cloud without EMF?
Absolutely, yeah. So all the components apart from EMF.cloud model server have no dependency on EMF. So you can just use them regardless whether you use EMF or not. And the model server you can also use without EMF. You just have to provide your own deserialization and serialization then to load those kinds of models. And I think practically you lose a lot of the functionality that is there when you use EMF, because EMF is very powerful, but you can definitely use it without EMF. And I have some examples of people doing that for particular reasons, because they have a legacy tool that just doesn't use EMF. So definitely yes.
Okay, thank you. Maximilian, it was fantastic having you on Cloud Tool Time.
Thank you very much for having me.
Before everyone goes, I just have a few important housekeeping announcements for you. So the next Cloud Tool Time will be on March the 30th, and it will be Jordan Pavlov. He's going to be talking about getting started with Eclipse Dirigible, which is also Cloud Dev Tools Working Group project. We would love you to click the green button that should appear any moment now at the bottom to give us feedback on this session. There it is right there. It says something like help us improve by completing the post-event survey. With your feedback, we can continue to iterate on this event and make it better for you. If you want to host a Cloud Tool Time yourself, if there is a particular tool, particular technology in this space that you want to talk about, or even that you would like to see but not necessarily talk about yourself, please fill out our form. The link has just been posted in the chat there. And I think that covers everything. So again, thank you, Maximilian, and to everybody who attended. We hope you enjoyed this Cloud Tool Time and hope to see you at future sessions. Thank you so much.
Thank you. Bye-bye.